Can you see my screen now?
Yes.
Okay. All right. So let's see the root. So the first question uh, has to do with uh, okay, the string. Okay. So I think this is the area that has to do with forces. So the question is, why does the weight of the person the cause the string to extend? All right. So I mean, the string will extend because weight acts downward. It's a force, and that's why it's different from mass. Mass is just a scalar quantity, doesn't have direction, but weight is a vector quantity. It has direction and it acts downward. So um, the answer for this particular one is the first one, which is weight acts downward. Okay. Um, okay. Maybe one more thing I need to say about weight acting downward is the fact that on the surface of the earth, like uh, everything seems to be attracted to the center of the earth. So the core of the earth. So there's a magnetic attraction, and that magnetic attraction, the acceleration due to gravity is what aids it. So that's the reason why weight is given by mass times acceleration due to gravity. Okay. All right, so we move on. Number two, complete the sentence. Choose the answer from the box. The weight of the person in figure one is A, gravitational, B, frictional, and C, electrostatic. Now, let's cancel out the ones that it could not be. It's definitely not frictional because it's not happening between two surfaces, okay, or between a hard surface and a liquid. In that case, that's viscosity. So it's not frictional. It's not electrostatic because it doesn't involve electric charges, static electric charges. So obviously the answer is gravitational. So it's a gravitational force. It's acting in line with gravity. Okay, this question seems quite straightforward, but you know, could be challenging too if you're not careful. The weight of the person causes an extension in the spring of 0.070 meter. Okay, so that's the extension. The question, the spring constant of the spring is 12,000 Newton per meter. It now says calculate the weight of the person. Okay, it says calculate the weight of the person. Okay, so let's see what needs to be there. Um, there's a formula that says weight is equal to spring constant times extension. So all you need to do, would they let you use a calculator in this question?
Yes.
Okay, anyway, for this one, we can do this one without a calculator. Just look at what's involved. Spring constant is 12,000. What you are multiplying it by is 0.070. The only thing I would say is this, apart from the simplicity of the multiplication, which will involve moving the decimal point in 0.070 three places to the right hand side because it's a multiplication, right? Because of the three zeros in 12,000. The other thing that you need to take note of is the unit. Okay, so if you look at the spring constant, the unit of the spring constant is Newton per meter, or like they usually say, Newton per unit meter. Then look at the extension unit is just meter. So they have to rhyme in terms of the meter. Okay, if they give extension in centimeter and they now give you because extension sometimes will not be that much, they now give you what do you call it? Uh, Spring constant in meter, you must do a conversion. And I will usually advise that you do the conversion on the side of the extension, so that the extension will match the spring constant. But in this case, we are good, so you don't need to do a conversion. For records, just remember that 100 centimeters makes 1 meter or equals 1 meter, so you know which direction to go, whether you are dividing by 100 or multiplying by 100. Okay, so in this case, like I said, all you just need to do is to move that decimal point 3 places to the right hand side, and then you will have 12 times 70 as the equivalent of that multiplication. And we know that 12 times 7 is 84. Okay, so 12 times 70 will be 840 by uh, uh, our 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 own method. So if you are free to say that the weight is 840 Newton. Okay.
Oh, yes.
All right. Did you got that right?
Yes.
Okay, sure. All right. So let's move on. It now says calculate the elastic potential energy stored in the extended spring, and just like the first one, they gave us an equation or a formula for the elastic potential energy is equal to 0.5 times spring constant times its tension squared. Okay, so here we go. I think this one, a calculator would help us, especially with the squared part. Okay, so I would advise that we start with the squared. So the extension is 0.070. So if we are to do this calculation, right, the first thing I would advise that we do is to find the square of 0.070. So um, could you, if you have your calculator open there, please help us calculate 0.070 square. What do you have?
0.14.
No, no, the square of 0.070. The square. Note, the square is not the same thing as multiplying it by 2. Okay, we're squaring it now, multiplying it by itself.
Oh, okay.
Yeah.
Yeah.
So what would that be? Now, if you can also still do this yourself without the calculator, but 7 times 7 is 49. So if you multiply 0.07, remember that zero after the 7, you can discard it if you want. 0.07 multiplied by itself, you have 7 times 7, 49. Then count how many decimal places are there, and then move the decimal point to the left according to the decimal places. So that would be 0.0049. You can confirm it from your calculator. 0.07 squared is 0.0049. Okay, are you
Yes.
good with that?
Yes, yes.
Okay, so I started with the square. So I've already done the extension square. All I now need to do is to multiply it by spring constant times zero point 0.5 or half. Now, uh, you can quickly do a calculation in your head. Half times 12,000 is definitely 6,000. So all I need to do is to multiply 0.0049 by 6,000. I'm doing my own calculation here too, but I need us to see if our values will agree. Times 6,000. So what do you have as your final answer? What do you have as your final answer?
84. Sorry, 840.
Okay, no, 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 no. I'm not talking about, we have moved from 1.3 to 1.4. We're on 1.4 now. 1.4 is elastic potential energy.
Oh,
Yes. Look at 1.4. The one that says extension squared. Have you seen it now?
Yes, yes, yes.
Uh-huh. So like I said, I first squared the extension, and that gave me um um 0.0049. Then the next thing I did was to multiply by the spring constant times half. The spring constant is 12,000. When you multiply it by half, you are halving it. That means dividing it by 2. So that is like 12,000 divided by 2. That's 6,000. Then I now multiply 6,000 by 0.0049. So what did you get as your answer now?
29.4.
29.4. That totally agrees with what I got too. So that's correct. So 29.4 um is 29.4, and the unit is in joules. Okay, because it's energy. Energy's unit is always joules. So that's the elastic potential energy of the extended spring. Okay, remember potential energy is energy by virtue of position. Okay, by virtue of position. So in this case, when the spring stretches, okay, it has a particular energy that is stored inside it. That is the elastic potential energy. Okay, so we're moving on. We're now on 1.5. If there is more than one person on the chair, okay, the spring could become inelastically deformed, and that means that it will lose its elasticity. So it will stretch and most likely become almost like a straight wire. Okay, it will, it will become deformed. So the question is, what is meant by inelastically deformed? Um, Number one, it says the spring extends more when two or more forces act on it. Two, the spring will not go back to its original length when the force is removed. And three, the spring extends so that it's twice as long as its original length. So the question, what do you think is the correct answer to that particular question? Inelastically deformed, what is the meaning?
Um, the spring
Which
went,
one would you go with?
I went go back to its original length.
Exactly. It will not go back to its original length. That's the whole meaning of it being deformed. And that's what is expected when you remove the force. It's expected that the spring will return to its original length, nothing less than that. But when that doesn't happen, then it's inelastically deformed. Okay, the manufacturer of the chair investigated the extension of a new spring, and it says figure 2 shows slotted masses hanging from the spring. The weight of the masses extends the spring. Yes. Okay, so what is the question? It says which length in figure 2 represents the extension of the spring. The extension is simply the difference between its original length and its new length. I mean, there's no big deal. So that's B. Okay, do you agree with that?
Yes.
Okay, all right. We're moving on. Um, Take a look at these graphs. The question is this: it says which graph shows that the extension of the spring is directly proportional to the force applied to the spring. Now, to the spring, sorry, not spring. Now, remember, I don't know if you remember in mathematics when we were looking at straight line graph, and I told you something that a straight line graph can only tilt in two directions, either towards the right hand side or towards the left. Now, the straight line graph is an example of a graph that shows you direct proportionality, the straight line graph, direct proportionality. And usually, if it's a case of one increasing when the other one increases, which is what direct proportionality means, then um, um, the graphs that would match that are going to be either A or B. Now, the question is, why is it that C and D are disqualified? It's simple. Number one, C is not a straight line. C is not a straight line, it's clearly a curve. So it cannot show us direct proportionality, especially with that side that is looking curvy. Maybe after the curve now becomes like a straight line going upwards, like a line facing towards the right, it now seems to show direct proportionality. But no, it's not. It should show it from the very beginning. Then D is not showing us direct proportionality at all. Instead, D is showing us inverse proportionality. Have you heard of those terms before? Direct proportionality and inverse proportionality.
Yes.
Okay, good. All right. So, the thing now is for us to establish which one is which. So, um, I would go with B. Okay. Now, let me say something about what A suggests. A is suggesting that even when there is no weight on the spring already has an extension. Do you think that's a good behavior for a spring? Hello, Noah, did you get my question?
Pardon?
Did you get my question? Did you understand my question?
No.
Okay, I said that D is showing us that when there's no force on the spring, there is equally no extension. That's why the graph starts from zero, from the origin. Did you get that?
Oh, okay.
Uh-huh. Now look at A carefully. You will see that A seems to intersect there's an intercept on the y-axis, which is the extension axis. What the interpretation of that is that even when the force is zero, that's on the x-axis, the force is zero, that there's already an extension on the spring. That means the spring already extends somewhat from its original length. Now I ask the question, is that a good behavior of a spring for it to have an extension even when there is no force on it? Did you get my question now?
Yes. No, no.
Okay, okay, no problem. The thing is that that would be an abnorm. Okay, it will be an abnormality in terms of the behavior of a spring. It should not extend when there is no weight on it. Okay, it shouldn't. There should be no extension. Okay, so moving on. We're on 1.8 now. 1.8 says table 1 shows the result of the manufacturer's investigation. Force in Newton 100, extension in meters 0.008, force in Newton 200, extension in meters 0.016. The question is this: suggest two improvements to the investigation. Two improvements to the investigation. How do we improve these investigations so that we can get accurate value? But let us even look at the investigation. I think um, okay, okay. Let me see. Where does it say? Okay, the manufacturer of the chair investigated the extension of a new spring. So, what do you think we could suggest to improve the investigation? Looking at it here, everything seems to be okay. Does the mark scheme give us any clue? Can you check what the mark scheme says for this part where it says two improvements to the investigation?
It, use a greater range of forces.
Okay, okay, use a greater range of forces. Okay. What's the second one?
Use forces that are similar to the weight of person.
Okay, forces that are similar to the weight of the person. Yes, that those are those are things that would actually improve the investigation and give more accurate behaviors, and values for the investigation. All right, so we're moving on. Um, this one is a graph of the movement of a car that records the movement of a car. It says a car contains a device called the black box. The black box records the distance traveled and the time taken for each journey. Okay, all right. So of course that means we can get the speed of the car from there. Okay. So the question says, which feature of figure 3 shows that the car travels at a constant speed for the first 4 seconds? Of course, constant speed means that you have a straight line, which means the gradient is constant. Simple. Constant speed for the first 4 seconds. The line is straight. There's no um um giving, there's no other option here that rhymes. It's the last one that's correct. Okay, please. The line becomes horizontal doesn't mean it's a constant speed. Okay, remember the first 4 seconds. If you look at it, it's showing you a line that's tilted towards the right. Again, showing us what direct proportionality. In this case, the distance traveled in meters is directly proportional to the time covered in seconds. Okay, so that's why we will go with the last option, that the line is straight. So the next question says, after 4 seconds, the driver applied the brake and the car slowed down and stopped. The car slowed down and stopped. The distance the car traveled after the brakes were applied is called the braking distance. Okay, so let's determine the braking distance of the car. So let's go to the figure 3 and determine the braking distance. So look at 4 seconds, right? Let's see. So if we trace it to the graph, what is the value there? Can you tell me what the value is there on the graph? What's the value for distance covered where the brakes are applied?
64.
64, correct. Okay, so that's 64 meters. Now, when the car comes to a halt, right, comes to a stop, what is the distance there? I think that's 84, right?
Yes.
Okay, so 84 minus 64 will give you what?
Pardon?
84 minus 64 will give you what?
20.
20. So that's 20 meters. That's the braking distance. All right. So, okay, now they're talking about the black box. The black box also records the deceleration of the car. It now says as the car decelerates, the velocity of the car changes by 16 meters per second. The car decelerates for 2.5 seconds. The question is this: calculate the deceleration of the car. Of course, deceleration is also the opposite of acceleration. Okay, deceleration. In fact, it's very, very correct to say that deceleration is acceleration in the opposite direction. Okay, let me say it again. Deceleration is the opposite of acceleration. And it's also correct to say that deceleration is the same thing as acceleration in the opposite direction. Okay, so they gave us a formula for deceleration here, which is change of velocity over time taken. So that's in this case 16 divided by 2.5. So what will that give you using your calculator, please? 16 divided by 2.5. What did you get?
6.4.
6.4. Okay. So let me just confirm it with my 16 divided by 2.5. Okay. All right. Correct. 6.4 indeed. Okay. So we're moving. So that's 6.4 meters per second squared. Okay. One more thing. I need to just say something about the unit. Okay, so take a look at the unit for deceleration. Did you see that it's carefully formed from the units of the things involved in it? Look at that. Change in velocity is its unit is meters per second. That is meters over seconds. Remember, meters is in the numerator, seconds is in the denominator. Of course, that makes sense because velocity is also speed. Okay, which is distance over time, meters over seconds. Then look at the unit of time taken. Time taken is also seconds. So that means meters over seconds divided by seconds. So that means you have seconds in the denominator two times. Okay. So because of that, that's why you have the unit of deceleration being what? Meters per second squared. Why? Because seconds times seconds is second squared. Okay. So I just thought to say that because uh, there's a part of physics that has to do with what they call dimension. I don't know if it's in a foundation scheme of work, but it's just good to know that the units of all those things always usually rhyme with their formulas. Okay, moving on. It says if the black box, right, records large deceleration, it identifies that the driving may be dangerous. Okay, so what could cause that? Why can large decelerations be dangerous? Really, if you think about it, right, that's why they usually advise do not hit the brakes too, um, do not apply too much force on the brake. Okay, uh, very large deceleration. So large, what does it mean? It means the brakes on the car can overheat. No, I don't think so. The driver may lose control of the car. So that's the whole idea. Usually to slow down the car, right? What? How do you a car that's on a high speed? What do? You simply you simply step on the brakes. You know, like subpedal it once, twice, thrice, until the car comes to a halt. But if one, in panic hits the brakes too suddenly, that car can flip. In fact, it's not, there's a very high likelihood that the car will flip because of the high speed that the car is on. So usually, um, um, it's always advised to do what? Brake the car severally if the car is on high speed and maybe something happens like tire skin stuff or something, something that the car in front suddenly stops or stuff something like that that would require you to um quickly halt the car. Okay, so um the answer to this is what? The driver may lose control of the car. All the other ones don't matter. The brakes on the car can overheat. I've never heard of that. The only thing is that the brake pad can, get um, what do you call it, can wear, suffer from wear and tear, which is a normal thing. The other option, the force applied by the brake is very small. No, that's not what can cause a dangerous deceleration. In fact, it won't even cause, it's not even dangerous to apply small brakes, forces to the brake. It's even advised to apply small forces, but then like, with small intervals. Then the reaction time of the driver increases cannot be the correct option. Thinking distance is very short. That's not what makes it dangerous. It's the fact that it was suddenly applied and, like all at once. Okay, so did you get my explanation back there? Hello,
Acceleration.
Noah. Did you get my explanation about why?
Oh, yes, yes, yes.
Okay, now, if you notice, there's something else here. This question says tick two boxes. So if you ask me to tick two boxes, I will go with the fact that the driver may lose control of the car. What do you think is the second box to be ticked in this? What do you think is the second box to be ticked here? Please take a look at it carefully before you answer. What do you think is the second box to be ticked here? Because there are two answers in this question. Some questions are like that.
I should say both of them.
Yes, select
The,
the second one. No, you don't need to look at the marking scheme. I want you to think about it. What do you think is the second um, answer here from this for this question? That's
no,
2.4.
okay. The brakes on the car can overheat.
Okay, so um okay, so you know what we'll do? We'll eventually check the max scheme for this. But I'm thinking about that last one, that the thinking distance is very short. Okay, but hey, I mean, it could, it may not be. I think it may not be. It may not be correct. But I'm very sure of that first one that I chose, that the driver may lose control of the car. Okay, so what does the max scheme say for that 2.4? What does the max scheme say for 2.4?
Sorry, I'm getting the marks.
Oh, okay, all right.
It says the last one and the first one.
Oh, okay. The last one and the first one.
Yeah.
Let's- The last one, okay. Thinking distance is very short. Oh, the brakes on the car can overheat. Really? Okay. Hmm. Okay. Okay. I'm just thinking overheat. Okay. The black box monitors the speed of the car. It says describe how speed affects braking distance. Describe how speed affects braking distance. Okay. So I think if the speed is too high, like the car is moving at a very high speed, the distance it will take to stop would be equally higher, isn't it? Because before the brakes can stop it, it may take a while to stop it when it's moving at a very high speed. But if it's not moving at, maybe it's just, the guy is just coasting, like driving the car gently and just immediately applies the brake, right? The car almost comes to a halt immediately, isn't it?
Oh, yes.
Okay, all right. Okay, so yeah, I think that's the explanation for that. If you see something more detailed in the mark scheme, um, also you could add that to your explanation. All right, we're now going to magnetism. Magnetism. Okay, so it says figure 4 shows iron filings sprinkled around a bar magnet. A bar magnet. Iron filings. Yeah. So those lines are the lines of force. What does it say? It said, why are the iron filings attracted to the bar magnet? For goodness sake, iron is magnetic. That's the only reason. Okay? Iron is magnetic. That's the reason why it's attracted to the bar magnet. The next question. Um, Figure 5 also shows a bar magnet. It says, draw magnetic field lines to show the magnetic field pattern around the bar magnet. You should add arrows to the field lines. Of course, if you don't add arrows, forget it. They are not field lines. There's no way they can be field lines. You should add arrows to the field lines to show the direction of the magnetic field. Okay, Noah, let me ask you. You have an idea of magnetism, right?
Yes.
In which direction do the field lines flow? From North Pole to South Pole or from South Pole to North Pole?
South to north.
Let me say it again. Do they flow from North Pole to the South Pole or from the South Pole to the North Pole?
Oh, north to south.
Okay, correct. They flow from north to south. And if you look at this first figure very well, you will see that those filings just simply arrange themselves according to the force field line. So let me just see if I can annotate. Well, I'm sure you will see a better diagram in your, what do you call it, um, in the mark scheme. But let me just see if I can attempt to draw how it would look. So you would do this, right? And remember to put the arrow there. Okay. So the thing is that around the North Pole, they seem to concentrate, then they seem to divide as they go round back into the South Pole, and they concentrate again at the South Pole. So let's just put the arrow. So this is how it will look. This is how it will look. Okay. So you got that right?
Yes.
Okay.
Wait, and then
All right.
should I draw the ones on the outside as well? Or just leave it.
Okay, this one.
Yeah.
Okay. Okay.
No, do you think they would want that as well? Or
Like this one.
yeah.
Okay. Yes, that's fine. But yes, so that's fine. So would add that just to show the direction of flow. Okay. So yes, that would be it. That would be the case. Okay. So moving on. Oh, sorry. Okay. The next question here says figure 6 shows two bar magnets, X and Y are used to denote the poles. It now says that the magnets attract each other. What conclusion can be made about the two poles marked X and Y? Now remember, just like in electricity, like charges repel and unlike charges attract. That's positive and negative. That's in electricity. In magnetism, the equivalent to magnetism is that like poles repel. That means north and north will repel, south and south will repel. However, north and south will attract. Okay, so if they told us that the magnets attract each other, it's obvious that one of them must be what? North pole and the other south pole. So the option we'll go with is that they are what? Opposite poles. They cannot be both north poles, they cannot be both south poles. Okay. For that to happen, they will have to repel. Okay. Okay. Hope you got that. Hello, Noah. Did you get that?
Yes.
Okay, okay, all right. I didn't hear you back then. Okay, so moving on. Um, this looks like an experiment. Okay, where we have a card with compasses that will show this is the magnetic field around a wire. Okay, around the wire because an electric wire too has some form of magnetism around it, and that's the principle on which your fan works. Things like your fan, things like what else? Um, things that spin powered by electricity. Okay, I'm just thinking about them, but anyway, you know what I'm talking about. Fans are simply they work based on electricity, an electric field, and then having an interaction with the magnetic field. But anyway, this one is just an electric field. Okay, so it says um, there is no current in the wire now. Why? Obviously, because the switch is open. You can see that from the diagram. The question now says, why do all the plotting compasses, why do the plotting compasses all point in the same direction? Okay, so plotting compasses, right? Uh, if I'm going to go with um, how compasses work, all of them are pointing towards the North Pole, right? All of them point towards the North Pole. So they are pointing in the same direction because, I mean, that's how they're designed. They are also, um, what do you call it, magnets themselves, and they will point in the direction of the North Pole. Okay. Why? Because there's no magnetism from the wire to distract them. I'm just using that word distract. Do you understand what I mean, Noah? Do you understand?
Yes.
Okay, good. All right. So let's look at what the next question says. It says, when the switch is closed and there's a current in the wire, the current creates a magnetic field. That is in itself a distraction. And then the question now is this: what shape are the magnetic field lines around the wire? Guess what? They would come out circular. Okay, they will come out circular. So that's that's how that's the direction they will come. And I think it's the right hand rule. I can't remember now, but it's the right hand rule that usually tells us um how the direction of those distance will be. Okay, the right hand rule. Okay, it is you just hold your right hand up and then do like you are doing a thumbs up. Okay, so the direction of your thumb is the direction of flow of current. Then your other fingers, okay, your other fingers that are grasped right in when you're doing a thumbs up towards somebody, they are going to show the direction of the magnetic field. Okay, so I don't know if you've seen that picture before. Do you understand what I'm talking about?
Yes.
Okay, okay. So if I'm not really good at, okay, let me just see if I can sketch, right? Yeah, and then look something like this. Mm, something like this. Okay, so your fingers being like this one show the direction of the field, of the magnetic field, while your thumb is pointing upwards, shows the direction of flow of the electricity. So just imagine that the wire is being held by the grip of this hand that is doing the thumbs up. So as the electricity is flowing upwards like this in the direction of the thumb, then the what do you call it? The magnetic field will follow the direction of the fingers. Okay. Well, my drawing doesn't look too accurate, but I guess you get the picture, right?
Yes.
Okay. So here we go. Um, so it's circular. The next question is something that deals with an experiment. It says the students investigated the force exerted by an electromagnet on a paper clip. Okay, paper clip. Let's see. Question. The student varied, okay, that's not the question. The student varied the distance between the paper clip and the electromagnet. Okay, okay, between the electromagnet. He changed the distance. Okay, so of course he was hoping that the to measure the effect of the magnetism on the paper clip, at which distance will the what do you call it, the magnetic force be strongest. Okay, so the question now is this: the current in the electromagnet was the same for each distance. It now says complete the sentence. In the investigation, the current was a control variable. Do you agree with that?
Yes.
Because it didn't change. Okay, we know control variables don't usually change. All right, next, what is the size of the downward force on the paper clip? So they say what's the size of the downward force on the paper clip? So, well, so can you see that this clip was um, attached to the spring? Okay, so that you can see the force of attraction on the electromagnet. You can easily measure it, so that if that clip was not stuck to the end of the spring there, it would quickly attract itself to the electromagnet, right?
Yeah.
Okay, good. So now that we understand what's really happening here, right? Let's read the Newton, what do you call it? The value on the screen. What's that value there? That's between uh, 3 and 4. I think it's 3.6. Do you agree? Should I
Yes.
zoom in? Okay, let's zoom in. It looks like it's 3.6, right? Because it's just right after 3.5.
Yeah.
Should I still zoom in again?
No, no, yes. Three.
Okay, so it's 3.6, right?
Yes, yes.
Okay, all right. Oh, sorry, I think I'm zooming out too much now. Okay, so it's 3.5. Okay, all right. So moving on, it says the distance between the paper clip and the electromagnet is increased. Now remember this, that when you increase distance, the effect of the magnetic uh, attraction will reduce. Magnets usually thrive on smaller distances between them and the thing that they're attracting. Okay. So if you increase the distance, what do you expect to happen?
Um,
What do you think?
sorry, my screen is still up.
Okay, okay. If you increase the distance between the electromagnet and the clip, what do you think will happen?
Uh, it'll decrease.
Yes, the force will decrease. It will decrease. So they're asking what happens to the size of the downward force? It's a decrease. Okay, so it's going to also decrease. Okay. Um. Okay. Now on to sound waves. Okay. So it says sound waves are longitudinal waves. Now I think just for reference, this section is talking about waves. I think in terms of classification of waves. Okay. Remember, waves are a form of energy passing through a medium, depending on which medium it is. And for sound waves, it's sound energy that they would uh, transmit. So waves always transmit energy somehow from one part in a medium to another. By classification, waves can be grouped into two. Can you tell me the second grouping, longitudinal and what kind of wave? What's the second group?
Um,
Do you remember?
no. No.
Okay, transverse. The
Um,
waves can either be transverse or longitudinal. Okay. Of course, from the word transverse, you can guess slightly what's happening. In a transverse wave, the direction of vibration is perpendicular to the direction of movement of the wave. Okay. That's why it's called transverse. It's like a trans thing. It's trans. It's cuts across. Okay. Think about a cross or a plus sign. Okay. That's how transverse waves look in terms of their direction. The direction of vibration can be vertical, while the direction of movement of the wave will be horizontal. But in the case of longitudinal, both the direction of vibration and the direction of movement of the wave are in the same direction. And that's what happens for sound. You can see, imagine when a speaker, I don't know that you've seen some of those animations where a speaker is producing sound and the speaker is going back and forth, based on the beat, the bass in the sound. And the sound, the air in front of the speaker's, what do you call it? The speaker is moving in the same direction of the vibration of the speaker. Have you seen animations like that before?
yes.
Okay, okay. All right. So, this figure shows a sound wave. The next question is this. It says we should choose the answers from the book. Um, where's the question? I don't see the question. Okay, complete the labels on figure 9. Oh, okay, okay. So, um, hmm. So what's which one is, one of them would be compression. One of them is a compression. The side where the dots seem to be clustered is uh, compression, while the part where between one compression and the other is an extension. Please help me confirm from the mark scheme if I'm correct. The compression is where the dots are clustered. That is the one on the left hand side. And extension is the one where the dots are a bit free, not so clustered.
It says compression and rarefaction.
Oh, refraction. Oh my goodness. Okay. Ah, okay. So yes, I was not too sure about it. That's why I said you should check the mark scheme. Okay. Refraction. Okay, that's fine. rarefaction. Okay, so it says which of the following is true for longitudinal waves? Longitudinal waves transfer charge? No. I mean, for goodness sake, why would a wave want to transfer charge when it's not carrying electricity? It's not transferring anything, any charge. Longitudinal waves transfer energy. I agree, full time. It's energy. I think I mentioned that in passing when we were talking about when I was just introducing longitudinal waves and waves generally. It's energy they transfer, please, nothing else. It's not even matter. I mean, the air that's in front of the speaker is not being transferred by the speaker's beating, it's not. It's the energy that's in the air that is being transferred from one point to the other. Okay, that's sound energy, of course. All right, did you get the explanation back there?
Yes.
Okay. Okay. It says figure 10 shows the device a farmer uses to scare away birds. Okay. This is interesting. Wow. It looks like it wants to look like the a camera or something, but it's not a camera. It says the device emits a very loud sound. Okay, to scare them, I guess. It says the farmer measures the sound emitted by the device at different distances from the device. Okay, what? Um, okay. So it now says figure 11 shows a visual display of the sound waves at different distances from the device. Both waves are drawn in to the same scale. Okay, so when it's a distance of 200 meters, did you notice that the amplitude would reduce? It looks like the amplitude of the waves will reduce. Whereas when it's a shorter distance of 80 meters, the amplitude of the wave, that's the height of those curves, will increase. So, so it says, what property? Oh, okay. What property of the wave changes between 80 meters and 200 meters? I think I've even said it somehow. The answer is amplitude. Okay, it's amplitude. Now, I like to usually do this. I like to explain why the other ones are not the answer. Let's talk about frequency. Frequency is the number of cycles in a second. The number of cycles covered in a second. Now, I'm not. I'm guessing. I'm not sure that this thing is is talking about time. But if you look at it very well, the number of cycles in both 80 meters and 200 meters is the same. I want you to take a look at it very well. Now, a cycle. Let me annotate. A cycle is simply between here and here. Okay, that's one cycle. So the next cycle will be here to here. So if you look at it, this guy has two cycles. A distance of 80 meters has two cycles. Distance of 200 meters also has two cycles because look at it. Here to here is one cycle. From here to here is another cycle. Do you understand what I just explained now?
Yes.
Okay. So the argument is that frequency cannot be the answer. That's what I'm just trying to say. Why? Because they will have the same frequency. Nothing changes as it pertains to frequency. Period is um I've forgotten period. I've forgotten period, but it cannot be the answer in this case. Wavelength is the distance covered by one wave. That's from here to here. That's the wavelength. Okay. And if you look at it, since they said that these graphs are drawn to scale, they apparently look the same. Yeah, because from here to here, if I draw a line straight, it looks to me that they will coincide, and they do coincide. And I draw from here to here, they do coincide. So what does that tell me? The wavelength is the same. I think that's the sign for wavelength. Is the same. Okay. But then the only one that is different is what? Amplitude. Why? Because amplitude is from here, the distance between here and here. Did you get that?
Yes.
Now, if you look carefully at this guy, the amplitude of this guy is, is higher than the amplitude of this guy. That's why this one looks like it looks smaller. It looks like it didn't go that high, whereas this guy went that high. Okay, so of course, it also happens for the second part of the cycle, which is here. Okay, all right. This is negative amplitude, of course, because of it's in the negative direction. Okay, did you get that? I just decided to take some time to explain because I'm not too sure. Of course, one question may never exhaust um, everything about a particular section of the syllabus, but it's all good. Do you understand what I just explained?
Yes.
Okay, all right. So moving on. This is figure 12. It shows the speed of the sound emitted by the device is affected by the temperature of the air. Yes, temperature affects sound. Temperature affects sound. As temperature increases, the speed of sound also increases, and it's a direct proportionality kind of thing. The question says the farmer tests the device on a day when the temperature of the air is 15 degrees Celsius. It says, what is the speed of the sound? Just go and read up 15 degrees then. So if you go to the graph and read it off, I think 15 degrees would be would be what? Can you read it off from your end?
Uh, 340.
340, correct, meters per second. Okay, on to the next. Still on sound. It says the farmer stands a safe distance from the device. Of course, the sound is about to really get huge. And then it says it takes a time of 0.20 seconds. I think this is echo that they want to talk about. Well, I'm not sure. It takes a time of 0.20 seconds for the sound to travel from the device to the farmer. That's for him to hear it. Calculate the distance between the device and the farmer. And the distance is given by speed times time. Of course, I mean, it can't be given by any other thing. So the speed of sound in this case, remember the speed we got from that graph was 340, right?
Yes.
So 340 times 0.20, what do you have?
68.
68. Okay, so that's 68 meters. Explain how the time taken for the sound to reach the farmer is affected by the temperature of the air. Okay, so explain how the time taken for the sound to reach the farmer is affected by the temperature of the air. Okay, so if we were to look at this graph carefully, right, the speed increases as the temperature increases. If speed increases, it means that the distance, um, the time taken for the sound to reach the farmer would reduce, isn't it? Something that's moving quickly would take a shorter time to get to its destination, right? Do you agree with that?
Yes.
Okay. So I mean, the explanation is a basic explanation. Just state it like that, and I think we're good to go. Okay, we're moving on and we're making progress. Okay, so it says figure 13 shows an engineer climbing up a ladder. Okay, that's the rung of the ladder where his feet are for him to be able to move from one part of the ladder to the other. It now says the distance between each rung on the ladder is 30 cm. That's about the length of a ruler. Yeah. The question is this: what is 30 cm in meters? Ah, this is a simple question. No? Just divide 30 cm by 100, because 100 centimeters make 1 meter. So by the time you divide by 100, the decimal point will move two places to the left. So that will become 0.3. Okay. Did you get that?
Yes.
Okay. I just asking you to convert. The next question. The engineer has a weight of 710 newtons. That's pretty heavy. Calculate the work done. Okay. Now work done when climbing from up one rung of the ladder. That's simple. Work done is equal to force times distance. So the force, his weight is a force. Okay, don't start thinking about what force are we talking about. It's his weight. So his weight 710 times 0.3. So can you help us calculate that quickly on your calculator? 710 times 0.3.
213.
213. Okay, so that's the answer for work done. Okay, and somehow, yes, the unit here is Newton meters, but guess what? Work done is also has a unit of joules. Why? Because I mean, just think about it. If you don't have energy, would you be able to do any work? That would not be a possibility. So energy also shares its unit of joules with work done. So just think about it. Whatever energy you have is what you will use to do the work. Okay. So apart from Newton meters as the unit for work done, joules is also a unit. I just thought to add that there just um uh for information. Okay. The engineer climbs the ladder carrying some equipment, extra weight. That's extra weight. It now says give the reason why carrying equipment increases the work done by the engineer while climbing the ladder. It's simple. That equipment now has extra weight, and that will be added to the weight of the engineer. So it's no longer going to be 710 newtons times 0.3. It's going to be 710 newtons in bracket plus whatever new weight of the equipment that he's carrying. Then when you add that together, you can now multiply by 0.3. Please confirm that you understood what I just said.
Yes.
Okay, brilliant, 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 brilliant. So moving on. It says the engineer is stationary at the top of the ladder. Maybe it stopped for some reason, and which energy stores the was let me take that again. Which energy stores of the engineer increase due to the engineer climbing the ladder? If you notice something, I've told you, I've mentioned the answer to this question today. If you remember, I don't know whether you remember when I told you about a particular type of energy that is available due to position of an object or due to position of a body. Do you remember when I said something like that earlier today?
Yes.
Okay. Do you remember the energy I mentioned? The type of energy?
Gravitational.
No. Okay. So it was it gravitational? Well, no. It was okay. So because of this work, right? I actually mentioned potential, right? But yes, it's safe for us to still call it gravitational potential energy. Okay. So yes, it's fine. I'll go with it. Gravitational potential energy. Please. It is not the other one. I mean, I can't even think of it as chemical. I mean, chemical is the kind of energy that is stored in a battery because of the electrolysis and all that. That's chemical energy. Elastic potential doesn't have anything to do with this. We're not talking about a thing. Kinetic energy is energy as a result of what? Movement. They didn't say while the guy was climbing the ladder. They said while the guy is still, you know, as it's going up, it's increasing. Okay, as it's going up, as it goes each round, it's increasing. Okay, but as it's moving one leg to the next rung, we can talk about kinetic energy. We're not talking about, that's not the one we're talking about. It says which one increases due to the engineer climbing the ladder. Remember, energy store. So it is gravitational potential. Thermal is out of the picture. That's heat. So, but did they say? Now let me be careful with that question. Two boxes I talked about. Okay, so fine. Let's see which ones are possible. So I'm sure of gravitational potential, right? Um, which other one is likely to be correct? Yeah. Okay. You know what? Let me fall back on the Max thing. What does the Max thing say about this one? Um, 5.4. Let's check. Maybe there's one that I underrated. Are you there?
Yes.
Okay. So what does 5.4? What does it say about 5 point?
It says thermal and gravitational potential.
Okay. Okay. No problem. Okay. Yeah. Okay. It makes sense. Heat, right? Heat, some form of energy. Yeah. As he climbs the ladder. Okay. Yeah. Heat energy. He's doing some work, so his body would, excuse me, generate heat. Okay. Wow. Now on to the next. It says write down the equation that links gravitational field strength. G, that's another name for acceleration due to gravity, mass and weight. Okay. So I don't know if they actually gave you guys or they will give you guys a physics equation sheet, but um it, when I remember writing physics, well, whether in O level, even as low as O level, they never gave us anything like a physics equation sheet. You have to memorize all your formulas yourself. I mean, you guys are really having it easy here with this question. So this is the formula. Okay. So weight is a force. So typically, from Newton's law, I'm not sure if it's the first law, but from Newton's law, force is equal to mass times acceleration. Okay. So it now depends on which kind of force you are dealing with and which kind of acceleration you are dealing with. You now have some variation. So when it comes to human beings and objects on the face of the earth, right, their mass will correspond with mass, but the acceleration that is in effect that is holding them down or attracting them to the center of the earth is acceleration due to gravity. Okay, so for us, that's why I said that time that weight is a force. Where does it act? It acts downwards, as in towards the center of the earth. Then mass is, and I said that it's a vector quantity. That means it has a direction. But mass does not have any direction. For instance, if I ask you what's your mass, you probably say 50 kg or something like that, right? Or 70 kg. Okay. But it doesn't have any direction, right? That mass can be moving to the left or to the right or even upwards if you are jumping. Okay. But your weight, standard weight, is mass times acceleration due to gravity. I think sometimes it's approximated to 10, 9.8, between 9.8 and 10. Okay. Then whatever you get is weight and the unit is Newton. Okay. So please confirm that you understood what I just said.
Yes, yes, I do.
Okay. So moving on. The engineer has a weight of 710 newtons. So yeah, of course, we've confirmed that weight. Question. Gravitational field strength, also known as acceleration due to gravity, is 9.8. Okay, I said that too. That's usually 9.8 or 10. Calculate the mass of the engineer. Oh, that's simple. So W equals, that's what we're going to use, mg. Okay, of course, m times g is something like mg. So 710 equals, I usually like to put this cross across my, that line, the dash across my 7, so that I know it is 7. It's like short thing. You can't miss it. Okay, so get your calculator ready. We're going to be punching the calculator very, very soon. So math, whenever in mathematics, whenever you have something multiplying what you are looking for, you simply divide both sides by that something. Okay. So in this case, I'm going to divide both sides by what?
7.
By what?
9.8.
9.8. Thank you. 9.8 is not the 7 thing, because it's not the 710 that is multiplying m. It's the 9.8 that is multiplying m. So you divide both sides by 9.8. Okay, so what does your calculator say? 710 divided by 9.8.
72.4.
72.4. And it says the two significant figures. That's going to give me 72, isn't it?
Yeah.
Okay, so that's it. We got it, we got it, we got it. So that engineer is pretty heavy, 72 kilograms. Okay, so are you good with this? Can we move on?
Yes, yes.
Okay, so again, sorry, I can't, because of the permissions on this file, I can't save the annotations. Um, they will be obstructing the other question as we scroll down. Okay, so we move. Uh, the next question says, the sun emits a continuous spectrum of electromagnetic waves. True? What is it saying? Uh, this names some of the groups of waves in the electromagnetic spectrum. Okay, so now the thing is that I'm not sure I remember the electromagnetic spectrum in detail. So maybe we'll have to depend on the max thing for this. So what does the max thing say for 6.1? What does the max thing say? Hello, are you there?
Yes.
Yes. So are you referring to the max thing now?
Oh, yes, I can't remember these. Shucks. I can read it.
Okay, go ahead. Read it. Let's see. A, what's A?
Radio waves,
Radio waves. B is
microwaves,
microwaves. Okay. And C is
X-rays.
X-rays. Okay. Radio waves, microwaves, and X-rays. Okay, so it says give one similarity. So please still hold on to that, because I'm not too sure I remember this either. Give one similarity and one difference between the properties of UV waves, UV waves, sorry, and gamma rays. So what's the similarity and what's the difference?
Um, Similarities.
Are they both transverse?
Transverse. Okay, yes. Electromagnetic waves are transverse, yes, in nature, yes. I agree with that. So, sequence.
Um, Gamma has a higher frequency.
Okay, gamma has a higher frequency than UV waves. Okay, okay. All right, so we're moving on, right?
Yeah.
Um, this looks familiar. Roy, yeah, I remember that acronym. Very popular acronym. What does it say? Um, light changes direction when it enters a glass using tube. That's refraction. What name is given to this process?
Um, ref Refraction.
Fraction, correct. That's the splitting of light, white light. Okay, it says use the, the physics equation sheet to answer question 0.64 and sorry, 6.4 and 6.5. Write down the equation that links frequency, wavelength, and wave speed. I think it's V equals F times wavelength. Okay, so that's the formula that links it. This is how it's going to look. Um, it's going to be V equals F times wavelength. Okay, so that's multiplication. Next, it says the wave in the middle of the spectrum has a wavelength of 5 times 10 raised to the power minus 7 meters. Speed of light is equal to 3.0 times 10 raised to the power 8 meters per second. It now says calculate the frequency of the wave. So if this is the formula for that connects V, F, and lambda, what that's the name of that symbol, the lambda. What will be the value of F? What will F be? F will be equal to what?
Um, the frequency. The
Remember,
frequency.
yes, that's the frequency. What will F be given by?
Oh,
Remember, I was trying
um,
to make a yes the subject of the formula.
V over
Yes,
wavelength.
yes, the wavelength, yes, or lambda. So that's going to, in this case, V is 3, that's the speed of light, 3 times 10 raised to the power 8, okay, okay, divided by wavelength is 5 times 10 raised to the power minus 7, okay. So how would you do this? 3 divided by 5. 3 divided by 5 is 0.6, right? Now I'm just trying to see if I can do this without a calculator first. And then when the calculator needs to assist us, we will bring it in. 3 itself divided by 5 is what? 0.6. Now look at the powers of 10. Do you remember those laws of indices that says when you have what does the law say? You have x raised to the power of a all over x raised to the power of b, that it is the same thing as x raised to the power of a, x raised to the power of a minus b. Do you remember this law? It's one of the laws of indices.
Ye yes, yes, yes.
Okay, okay, good. So let's apply it. So this will now be equal to 10 raised. Take note, the guy on top, his own power will come first. 10 raised to the power 8 minus minus 7. This is how we're going to write it. If you are writing it down if you are showing your working, this is how you are going to write it. 8 minus minus 7. And we all know that minus minus, the minus and the minus in front will become plus. So that will now leave me with 0.6. Um, you know what? I'm thinking of the easiest way to do this thing. I like to make things easy. Oh. I don't like something stressing me. If I can avoid it, I usually avoid it. Anyway, okay, no problem. Let's continue. Let's continue. We'll still find an easy way around it. So that will be 0.6 times 10 raised to the power of 8 plus 7 is 15. Did you get that?
Yes.
Okay. Now, you know this thing is not in standard form yet. I hope you know that what you're seeing here is not in standard form. So to make it standard form, we're going to take one of the 10s from this 10 raised to power 15 and
Wait.
multiply by this 6. That 6 will become 0.6 will become 6.0. You know, anytime you multiply something by 10, the decimal point will move to the right hand side 1 because there's only one zero in 10. Then the 10 raised to power 15 will now become 10 raised to power 14. Do you understand what happened back there? Do you understand what happened back there?
Yeah, no, because I had finished and I got 10 to the power 14. That's why I was about to ask.
Oh,
Yeah.
okay, nice. Did you use your calculator to do that?
Yeah.
Okay, good. Okay, that's good. At least your calculator will help you to do standard form. Okay, that's good. Nice job, nice job, nice job, nice job. Okay, so okay, okay. So just trying to get this guy off my page so that I can move on. Okay, so here we go. Um, okay, we're getting very close to the end of it. A student investigated how the acceleration of a trolley is affected by the force acting on the trolley. Okay, the trolley is affected by the force acting on the trolley. Okay, so it looks like, okay, it shows some of the equipment used. So the question is this. Describe a method the student could use. Your answer should include any extra equipment needed. Okay, so I'll leave you to um consume this from the mark scheme because it has to do with the process. But uh, um, um, the student is investigating how acceleration of a trolley will be affected by the force acting on the trolley. You know, when you're you just imagine you're in a car that's moving downhill. You notice that it looks like there's an extra force acting on the car apart from the force on the engine. The car will seem to move faster if it's going down a road that's sloping downward, okay, versus when the road is when it's going up a hill or going up, you know, what do you call it, a high place. Okay, so I'll leave you to take that from the mark scheme. let's let's look at the next question. It says table 2 shows one set of results for a similar investigation. Resultant force in newtons, acceleration in meters per second squared, 1.2 versus 1.6. Question: which of Newton's laws predict that the acceleration of a trolley is proportional to the resultant force on the trolley? Okay, so Newton's laws, I remember them in the exact order. I know that one of them says that for every action there's an equal but opposite reaction, right?
Yes.
I think it's the first one that says every every object or an object would remain in a state of rest or constant acceleration until it is acted on by an external force, right?
Yeah.
That's another of the law. I think that's the first one. So if the first one says that, then obviously it should be the second one that tells us that the the acceleration of an object is proportional to the resultant force on that object. So I think I'll go with second law, but help me confirm if the Max scheme agrees with us. That's for 7.2. Does the Max scheme agree?
Yes.
Okay, good. All right. So moving on. Okay, this one is a question. It says determine the acceleration of a trolley when the resultant force is 3.6. Okay. Okay. So did they tell us the weight of the trolley?
No, you
Okay.
can
So
do the opposite.
let me go back up there. It doesn't. They didn't say
Yeah, yeah, you do the opposite.
the opposite. I didn't get it. Why did you say the opposite?
As in, uh, because to find the
Oh, don't worry. I understand. I understand. So 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 this is what they want us to do, right? They didn't give us. Did you notice that they did not give us the mass of the trolley? Did you notice that?
yes.
Okay. So this is the whole idea. We are going to use this table, but we have to find the mass of the trolley first. So force equals mass times acceleration. Okay. In this case, now we're not dealing with the weight of the trolley because it's not in the downward direction. It's not weight that we're talking about. So let's find what mass will be. Mass will be equal to force over acceleration, force divided by acceleration. And that, in this case, going to be equal to 1.2 divided by 1.6. What would that give you, please?
Wait, is it not
What would that
0.75?
give? 0.75. Okay. So that's going to be the mass of this guy in kilograms, the mass of the trolley in kilograms. Now, um, let's move down a bit. So they now said we should find what is the acceleration of the trolley when the resultant force is 3.6. So this time now, these things will slightly change because acceleration, we're no more looking for mass now, we're looking for acceleration. So still saying that F equals ma, F equals ma, right? Acceleration, therefore, acceleration will be equal to F over m, F over m, F over m. So that's going to be resultant force in this case. Now remember, it's not in the former case. This particular case is 3.6. The mass will not change since it's the same trolley. So that's 0.75. Did you notice that I did not convert the mass to grams?
Yes.
So we get kilograms. Okay. So 3.6 divided by 0.75 will give you what?
4.8.
4.8. Thank you. 4.8 meters per second. Okay. On Newton per kilogram. Okay, whatever it is. All right. So we're good with this.
Yes.
Okay. Let me quickly erase this guy so they will let us proceed to the next page without obstruction. All right. Okay. Okay, next. Write down the equation that links acceleration. Oh, I've already written it down now. Well, that's what we used to solve that guy back there. F equals ma. A resultant force of 0.42 Newton, right, acts on a different trolley. This time, the acceleration of the trolley is 1.2. Find the mass. Ah, same thing. So we are going to still do the same thing we did back then. Only this time we are looking for the mass. So F equals ma. Therefore, m will be equal to F over a. F over a. And that would give us what? 0.42. Help us crunch this. 0.42 divided by 1.2 divided by 1.2. What did you get? To be 0 point something.
0.35.
0.35. Okay, and it's in kilogram. Yep, we got it. Okay, so are you good with that? Can I proceed?
Yes.
Okay. Okay, so please don't forget to send me the marks in maybe when we're done. Okay. Oh, it looks like we're done already. Okay, yeah, we're done. Okay, so these questions were quite interesting. This paper 2 is actually pretty straightforward. Okay, so for tomorrow's class we'll do 2022, right?
Yes.
Okay. All right. So, oh, okay. All right. So I think we've been able to use our time well today. I don't think there's any question that I left unattended to. But yeah, if there's any, just quickly hit me up on WhatsApp so that I can try to resolve it. Okay. So um I think okay, yes, the only one that we did not do was that one that had to do with the procedure, steps, steps for the trolley and stuff like that. So, what needs to be added to make it um to make the experiment work? All right. So you're good, right?
Yes. Thank you.
Okay. So I'll be
If,
waiting for the map. Sorry,
uh,
what did you say?
yeah, if you could send one of these slideshow things, please. For other
Oh,
people to.
okay. Okay, okay. All right, no problem. I'll look. I'll do that. I'll do that. I'll do that. Okay, I'll do that.
Yeah,
Yeah, I'll send it. I'll send it as I'll convert it to PDF and I'll send to you. I'll do that. Let me do that now so that I don't forget. Okay, so enjoy the rest of your day.
thank you too.
All right, bye.
Bye.